Good afternoon, everybody. Welcome to the Digital Twin presentation of the Mechatronics Transfer System and Top Loader. Our project group is composed of me, myself, Remy Bos, and my fellow students Samuel Jarvis, Casper Metzemakers, and Arjan Vreugdehil. During the presentation, we will go over a few topics. The first would be the product owner's point of view, where we will briefly introduce you to the problem description and the goal for the project. We will then introduce you to the MTST, to the physical machine, such that you have a bit of an impression of how it looks like, how the different hardware components interact with each other, and how it operates. We will then move on to the system requirements, which are the requirements that we, together with the product owner, came up with. We will then cover the process on how we approached each of the requirements and what we came up with. And then finally, we will display the results of the system that we designed and came up with. Finally, we will then demonstrate the actual digital twin. From the product owner's point of view, the concept or the problem was that creating a digital twin is often quite technical, time-consuming, and expensive. And a digital twin then means that it is a virtualized version of a physical system. So in this case, it would be the mechatronics transfer system and the top loader. And the primary research question, as we defined it, was how can we create a digital twin of the physical system, and how can this be done easily, quickly, but also efficiently? And by quickly and efficiently, we pretty much mean that a project group can do it in a short period of time, applying some tools that are pretty easy to use, I would say, that they're well documented, and that pretty much an IT professional should be capable of applying the same tools and figuring out a similar way to create a digital twin of a system. I've mentioned the system a few times, the Mechatronics Transfer System and Top Loader, or the MTST as short. This system is displayed in the image that you see on the screen, which is comprised of 3 lanes, and these 3 lanes are driven by physical chains. And at the end of each of these lanes, you see those blue elevators. And each of those elevators have some small belts on them. And together, this system is responsible for moving a pallet or a tile, which is the black square that you can see on the right of or underneath my cursor, which is transferred over the chains. And there's several sensors and actuators or inputs and outputs that are connected to a PLC. And these inputs, which are fed to the PLC from different sensors, will be logically evaluated by the PLC based on some programming logic. And the PLC will in turn set different output values, controlling, for example, a stopper that is responsible for stopping a pallet. So those are a few examples of how the physical system at the location would work with a pallet on it. Which brings us to the system requirements, which we, together with the product owner, came up with, of which the first system requirement would be that we have a way to aggregate the data or the input and output values of the PLC in real time, and also have a means to log those values. Because if we have access to those values, we can also use them as an input to the virtual environment. And because those values map exactly to the physical machine, if we have them in a virtual environment, we can also create a 2D or 3D representation of the physical system, which would then act and behave in the same way based on what we program with those values. And of course, those design and tooling decisions, or the tools that we were going to use, were all researched and documented as well, and how we came to the conclusion that one would be a better choice for us or the way to go during the project. And eventually we also created a user manual to indicate what we did, how we approached it, and how other future students might use our system or expand on it, as well as some topics they could further research on. So that brings us to the project process. The project process was comprised of 3 phases, and of which we already briefly mentioned 2 of those, which was the data aggregation and logging phase, then the virtualization phase, or the digital twin, and finally it was also a goal to control the physical machine through its digital twin. And each of those three phases we approached in a similar manner, of which for the data aggregation, we pretty much went on a search for means or ways to aggregate data from a PLC, and in more specific, the Siemens PLC that we were working with. And that resulted in several options, of which we had an MQTT library, which we could deploy on the Siemens PLC itself. It was also a library provided by Siemens. But because of the nature of TIA Portal and the, let's say, learning curve that was related to it, we, after making a small experiment, decided to look into another tool. And the other tool that we had was PLC4X, which was an open source library provided by, or under the Apache umbrella, I believe. But yeah, creating a simple experiment or proof of concept using the Java programming language quite quickly resulted in an access denied error. So there was something up with the PLC or some configuration on the PLC that we couldn't really figure out through the documentation of the library, which ultimately led us to take a look into Node-RED, which had libraries exactly for the Siemens PLC through a library called S7contrib, which allowed us to actually create a flow-based program, which was pretty high level and self-documenting because it describes a flow of data, which actually turned out to be the most clean solution for our project and also gave the quickest results in the shortest period of time. So the virtualization was pretty much a similar kind of process, except that we already had a bit of an understanding of some tools that we could use to create a digital twin. And initially we wanted to create a fairly basic or simplified digital twin. So that would be in a 2D representation of the machine, which we would either create through a tool called Streamsheets. I believe it's called Eclipse Streamsheets. And that worked pretty well, but we came to the conclusion that we couldn't import any images into it, so we couldn't really reuse some of the nicer top view images that we have that we could use as a representation for the digital twin, which would mean that we would have to create all of the components ourselves just using basic shapes that the Streamsheets program provided, which would be quite hard to maintain, also quite hard to extend, and it would give a really simplified visualization of the physical machine. And because of that, we also took a look at programming a digital twin through a Windows form using Visual Studio and C#, which we already, of course, had some experience with because it is integral part of the education. So that turned out to be quite a nice way to at least get a simple version of the digital twin, because we could use the top view images as a background, and on top of that image we could add extra additional form controls that we could then manipulate based on the sensor data that would be provided to the application. So that gave quite a nice simplified but not too simplified virtualization of the physical machine that we ended up with. And finally, because the time was pretty short or limited at the end, we didn't get to look into controlling it remotely, unfortunately, because we were fine-tuning the visualization of the digital twin. Which brings us to the results. So on the left we can see the system that we created in a top-level overview, where we have an IoT 2050 device, which you can see here in the middle, which is actually more or less a industrial Raspberry Pi, which was provided to us by Siemens. That was really kind of them as well. And on top of that device, we deployed a Node-RED application together with a Mosquito brokerage. And the Node-RED application is programmed in such a way that it pulls the PLC of the machine, extracting all of the data that is available of every input and output that is available on the machine. And for each of those inputs and outputs, we then publish it to the brokerage, such that other client applications can listen to the brokerage and also obtain the same data in real time. And on the right, you can see the actual Node-RED application that is running on the IoT device, which is fairly basic. We see a node that is responsible for extracting data from the PLC. Then some formatting happens, and then finally we see that it gets published to an MQTT broker. And at the bottom we then see the actual Windows Form application that is our representation of the physical machine. And what we can see is the top view of the transfer system in a 2D way, of which we see 3 lanes with the chains, the belts, the elevators, etc. Which brings us to the demonstration, where we, of course, will show a working example of the digital twin that we have created, so that you get a better impression of what I just briefly mentioned.
To briefly explain what's on screen at the moment, in the top half of the screen is our Windows Forms digital twin, and in the bottom is the physical transfer system with a pallet on it running a test case cycle. As you can see, there are still some visual bugs in our digital twin. Specifically, the pallet proceeds off the screen. However, for the most part, the digital twin accurately mimics the physical transfer system. Do keep in mind that the digital twin and the physical transfer system are reflected, and so the pallets are moving in opposite directions.